Okay, we're about to kick off again, so please have a seat. And the next speaker is Lars Liman. I think we met before. He is from Netnod and he's going to talk about the recent DDoS attacks that we've experienced.
Yeah, this might seem to work. So, it's going to be a slightly longer expose of DDoS attacks and what we've seen and what we see and what we do about them and how we interact with others. So, excuse me, having coffee just before we're going to give a presentation isn't always the best. So, lastly, as I said, I've been in Netnod for quite a while. I would be surprised if there's anyone in the audience who don't recognize me by now. DDoS attacks. So, Netnod services, we, as you know, provide mainly two types of services. We have the exchange points and where we haven't seen much abuse of these services over the years. We've been doing it for 20 years now, and the number of cases where people actually have abused the actual exchange point services is absolutely mute. On the other hand, we also provide infrastructure services on a wider scale, and there we have, of course, our DNS services, our root name server, and DNS services for local domains and other important domains. And we also have the NTP services. Now, Raggi already talked about the NTP services and what we're doing there, so I'm not going to focus on that. I'm going to focus on the DNS side. On top of that, we of course have the normal company mail, web DNS provisioning systems, customer portal, and what have you. But these are very small systems, so they are not really useful to the miscreants. You will note that both NTP and DNS are UDP-based services. And that makes them extra vulnerable, so it's very easy to forge packets, so rather to forge the sender address, the source address of these packets, and that will create the reflection attacks, which we will update. We have a bit of a problem because our services are supposed to be public. We cannot really narrow it down. We said, no, you're not allowed to use the root name server. No. Doesn't work that way. And again, our time servers are there to provide time to the general public. So, in order to close anything down, you will have to have a very good reason to do so. We have more than 300 powerful public servers spread across the globe. That's a fair amount of horsepower out there, and they are all quite well connected. They sit at exchange point or at major ISPs, so they can actually pump out a lot of traffic. And that makes us a bit of a juice target for certain types of attacks. The underlying problem, I would say the big underlying problem for these type of reflection attacks is the overall unwillingness to implement BCP38, which is a document that specifies how to filter incoming packets from your customers when you are typically an ISP. So, if you've never heard about it, this is a good time to look up the URL there and have a look at it. It's not that hard. That said, I think that Swedish ISPs are not at the head of the problem. Excuse me. So, if we focus a bit on the DNS side, we see two types of attacks. One is the typical denial of service by overload, and these are attacks that where our services are actually the target for one reason or another. These happen in types of just traffic load. People just throw a lot of packets at us and hope that will take out the service. When these happen, we see traffic from a variety of sources. That would be your typical botnet attacking. We have this variety of sources where each source sends a small trickle of attack traffic, but it adds up as you get close to the server. Many times they ask for the same data because the software in the bot is seldom very intelligent, so we see the same query coming in. Sometimes it's more elaborate, there's some variation or some randomness in the queries. We had one interesting case which we didn't know at first. We saw reports from other DNS operators that were seeing DOS traffic, and we didn't at first, because we looked at our query graphs and there was no significant change. Nothing happened until someone said, "Have you looked at your traffic graph?" So we looked at the routers instead, and it turned out that yes, we were under heavy attack, but the things coming in were not queries, they were responses. And so people were sending responses to our DNS servers. So they received and said, "This is not a query. This is not a query." And since they were not queries, they were not counted in the stats. So they didn't show up in the graphs. So we adapted our monitoring procedures after that. And then we have the typical reflection attacks, where we're not a target, we're just a convenient tool to hit someone else, and that's where our big servers come into play. Here, of course, the source address has to be unique because you want all the traffic to hit a specific target, which means that when it arrives to us, we bounce it off back to the address that seems to be the source, which is isn't, but we can't know that. And here we often see a unique query string with a big amplification factor, meaning a very short DNS query, which leads to a very large response. So we have an amplification in the DNS server. This is growing over time. If we go back, this is from January 2015, so this is more than a year old. We had a couple of significant attacks. We see here up to 300,000 queries per second. This is on overall of all the DNS servers traffic graph, and you can see that these spikes are typically rather short. We're counting hours here, not days, because it's difficult for them to maintain that level of traffic for longer periods of time. But the botnets are getting better, it's getting more powerful, so note that these are different timescales. This is a monthly picture, and this is a weekly picture, and you'll also note that the y-axis is different, so this one reached up to 500,000 packets per second. That is like, as a friend of mine put it, that's like reading the newspaper in a blizzard. You can't really even store all that incoming traffic, so you have to take samples of it, but with 500,000 packets per second, any sample will be good enough for your post-mortem analysis. So, what do we do? Of course, Anycast is our big tool for dealing with this. We, as you know, have servers spread all over the globe, somewhere between 50 and 55 sites active. And in most of these places we have a number of machines, so that can swallow a whole lot of traffic. Unfortunately, when we have attacks, they're not evenly distributed. They are distributed, but not evenly. So our servers in the very far-off corners of the world, they don't see much DOS traffic because they don't attract the traffic. The Anycast model is dependent on the underlying routing infrastructure, and unfortunately the routers don't realize that they should even out the load by sending the traffic to Bhutan or Vanuatu or these off corners of the world, seen from here at least. Anycast swallows the load, but it also helps creating a better reflector for reflection attacks. So we end up with this philosophical question, so which is more important, to keep the service going or to protect the poor victim of the reflection attacks? You will have to try to strike a balance here. It's not always that easy, but we can't really turn off the service because we have customers that pay for providing this service, especially in the NTP case, also big TLDs that really pay us to provide the service. But on the other hand, we don't want to be the party that creates this high impact on some poor victim, which we don't have a relationship with. So we really usually don't know who it is or why it's happening or anything. It's just our machine is bombarding them with packets. So the typical way of dealing with this is rate limiting, and it's kind of a middle ground, a compromise. You do that by dropping packets selectively. I guess most of your technical people in here have dealt with this, which means that we send far less traffic towards the victim, but on the other hand, we also lower the quality of the service. We degrade the quality of the service for those who are within the profile that gets rate limited. And of course, the hope here is to keep everyone alive, degraded but alive, which is often better than not working at all. That can be debated, and it depends from situation to situation. Sometimes being totally blacked out is actually better because that switches over to some different service. But this is at least the underlying philosophy for rate limiting. Now in DNS there are two ways to do rate limiting that are commonly available. One is to do the rate limiting in the operating system, in the kernel, and the other one is to have the DNS software do it. And if you look at rate limiting in the kernel, it has a few advantages. One of them is that it's extremely resource effective, which means that it doesn't take a toll on your computer to any larger degree. It can throw away packets at an alarming rate if you configure the kernel to just drop them. And it also has the small advantage that the configuration for the rate limiting is independent of which DNS server software you're using. So regardless of whether you're using Bind or NSD or not, or what have you, you have the same configuration for the rate limiting. The disadvantages are more. It's rather inflexible because these kernel packet filters are not very good at understanding DNS. So it necessitates compiling hexadecimal strings that you need to tell the kernel, look for this exact bit pattern, and if you see it, then apply your rate limiting algorithms. Now that is changing as these modules are being developed. You see more and better modules that are specialized in dealing with DNS, but it's still a rather rough territory. And these fixed bit strings are not very well suited for attacks with varied DNS content. If you have varying queries or varying addresses, this doesn't really work well at all. It's also very labor intensive and slow. You have to look at the packet, you have to devise these strings, and you have to deploy them on all the servers, so that takes a while, and it will cost you a lot of manpower. It's a daily manual thing. And the parameters for doing the dropping are also fairly basic. Setting how and which packets to drop is not very flexible. So if you move along to the other alternative, is to do this in the DNS server software, and it has a lot of advantages because that server typically does understand DNS. That's what it's there for. So it can be much more dynamic. The software is typically much more powerful than the kernel in its flexibility. And it can handle large databases of metadata for these dropping profiles. It can typically keep track of who sent how many questions under which time period regarding which domain names, and build up databases and timing there, so it can have a very fine-grained understanding of who's attacking and what does the attack look like. The drop parameters are typically more flexible, or that also comes back to the more flexible and powerful software. And it can be more automatic. You can have thresholds in this database saying if you have traffic volumes that exceed these thresholds, you should kick in automatically. And of course, this all leads to a less labor-intensive configuration. The disadvantage, though, is that it's much more expensive computationally, and your server takes a bigger performance hit. Then again, things develop, that's getting better. So I guess the future is on our side here. So in Netnod's case, going back, we have been working with Ratelimiting in the kernel, and we're fairly happy with that, but as attacks change and also as software develops, we're starting to look more into doing this in the server software. And some of the reasons are because we see more attacks, because the software is getting better and more flexible, because we want to save on manpower, and so on. So there are a lot of things that should speak to this. Apart from working with this ourselves, we do cooperate with other organizations, and we do that to a very large extent, actually. The most obvious one is for the root server. We do work with the other root server operators. I'll set a picture of that. We do work with other groups that are focused on DNS operations. You will see the right as the DNS working group. DNS-ORC, the Operations Analysis and Research Center, which is a very narrow DNS-focused organization. We work with them a lot, and they are a vehicle, a platform for creating discussions and developments for DNS operators, of which the root server operators are very obvious members of that community. And they also host various tools for researchers who want to do research on DNS traffic, DNS functions, DNS qualities, and so on. We'll get back to that as well. And we are involved in ICANN as well. I'm a member of the Root Service System Advisory Committee to the board. We deal specifically with questions regarding the root service and how that ties into the policy models that ICANN developed. Patrick is one of the chairs. Is the chair for the Security and Stability Advisory Committee, which has a wider scope looking at the security and stability for all aspects of it for the internet. And we're also involved in a group called the Technical Experts Group, which is it's a bit of an ad hoc group that has a wide variety of technical experts to hold discussions regarding the technical operations that ICANN are involved in, and also to respond to questions from the board. But it's not such a formal structure as RSAC and SAC. It doesn't have a typical chair, it doesn't have a typical relationship with the board as the other ones. Of course, involved in the ITF, because some of these things actually come back to the DNS protocol itself. What can we do with the protocol to make it more robust, to make it more resilient, and that ties into the DNS op and previously DNS extensions working group. That working group is now dormant because they were done. The ITF tends to think that from time to time that we are done with the DNS protocol. It usually stays that way for a year or two, and then they realize, oh, there's more work to do, and they kind of revive the work and keep going. So I expect that to happen in a year or two. And also close cooperation with the software developers. The System Consortium, of course, NTP Labs for NSD, and NIC CZ for the non-DNS. And other domain registries. The larger one typically have a lot of DNS clue, and we're all engaged in trying to fight the same war. Apart from that, we also have some preparedness when it comes to crisis management. We have 2 members of the National Telecommunications Coordination Group here in Sweden, which is a group set up by the regulator to facilitate restoration of service if we have a major disaster of some kind. And this group is comprised by ISPs, telecoms operators, and also people from the power sector, electrical power, because that's always needed. And there's actually a mutual tie between power and telephony, because, for instance, the base station for mobile telephony won't work without power. On the other hand, the guys who repair the power lines after a storm, they need telephones to be able to synchronize their work. So there's a mutual interdependence there. And if one set of repairmen go this direction geographically and the other guys go that direction, nothing will happen. But if they work in the same area, for instance, you can restore things more quickly. At least that's the theory. And we also have certain members of the management team and a few others in the staff having attended training courses in crisis management. Part of the work is also to collect statistics, and we now, for instance, have two things that are related to the DNS OARC group that I mentioned before. We take part in something called the Day in the Life of the Internet, the DDOS, which are 48-hour time slots that happen once or maybe a few times per year, where we record, as well as we can, we record all incoming DNS queries and store them. And then we upload them to the OARC database for researchers to look at in the future. And they retain historic data for digital recordings for as long as they have happened, which is 4 or 5 years now, I think. The starting point for this, the triggering factor, was signing the root. When the root was about to be signed, the DNSSEC. Digital was performed as a way to establish the baseline. What did it look like before signing the root? What does it look like after signing the root? So is there a difference? Are the different behaviors in the systems, in the servers? Do we need to watch out for something special? RSAC 002 is actually along the same track, but it's continuous. RSAC 002 is a document which is issued by the Root System Advisory Committee of ICANN. It specifies a number of measuring points that the root server operators are expected to watch. Typically query levels, sizes of responses, root zone size, delays in the systems and stuff like that. And the idea is to collect these over a long period of time, so you can look at long-term trends, see what happens when we deploy new GTLDs. Do they somehow disturb the root server system, and are there any alarming signs or factors? And that comes out as a result of a root scaling study that was undertaken probably 6 or 7 years ago by now. On top of that, we also do packet dumps for future analysis. These are a little more random. We do retain query dumps for a certain amount of time. So if we have some kind of anomaly in traffic, we can look at what happened, and we can investigate the data, at least recent data, and how recent depends on the load of the server. And we have some homebrew tools to look at this. Some of these have we developed with DDOS, and these have been presented here before. The root server operators. These are actually rather well-established contacts between these. 12 organizations. They all have very good experience with these operations, and these are all extremely varied. They range from small organizations with 20-odd employees, like Netnod, which is a not-for-profit but still a company, to places like the US Army Research Lab, or the US Department of Defense Network Information Center. They have typically different resources, but they also have different decision paths. For Netnod to make a decision is fairly quick. I walk up to Stefan and say, we need to do this, it will cost this much, and he'll say yes or no, and we're done, we do it. It doesn't work that way at the Army Research Lab. The procurement cycle is typically a couple of years. So we're very different organizations, but we are all very focused on operating the root service. All the actual people who do operate the servers are first name basis with each other, so I all know them, and when I speak to them on the phone, I recognize the voices. They have the telephone numbers that make the telephone next to my bed ring, and usually so. So we have a very close-knit group of people here who work very well together. We have regular meetings 3 times per year where we go through technical problems or things that we want to change and develop in the system. And on top of that, we have emergency meetings if that needs to happen, which is extremely seldom. We have a pre-configured system that will dial out to all the technical members of the root server operators from all 12 organizations just by pushing a button. It has happened to me. I've been out there buying Christmas presents with my children and suddenly it goes off and I'm on a telephone conference regarding some operational emergency or a test call, which is what you hope for in the toy shop. We also have secure systems for sharing information. You call it Wiki systems, where we can share packet dumps, we can discuss things, upload stuff that we need to share. Of course, other types of communication like Jabber servers, email lists with automatic PGP signing and everything is just there. And we use this to share information among each other. There is very little competition when it comes to the stability and resilience part between the root server operators. We can compete in other areas, but we don't compromise here. This is too important to just fiddle with business stuff. This needs to run. And we actually also conduct crisis exercises with the regular intervals. So we sit down, we have a table exercise, or it can even be distributed. We are home in Stockholm, someone else is in California, and a third person is in Amsterdam, and have these telephone calls as exercises with prepared scenarios and what would happen, how would you interact, what would you say to the press. So all of that is kind of tied into these exercises. I was actually going to stop there. Are there any questions? Anything I can help you with? Actually. You need a microphone. I'll just off this one to take that one.
Yes, so this is Mehmet Netnod. If you go back to slide 12, I would like to clarify. You said that we collect data for the digital, and just to point out that we upload the data only for iRoot. We only do it for our customers if they ask us to do. And as we would like to comply to European data privacy legislation, we anonymize the source addresses before we upload, so we try to keep to the regulations.
Thank you. I should have put that out.
Any other questions or comments? Yeah?
I suppose that you use a layered approach when you protect your Anycast servers from overload DDoS. And I suppose that you both use kernel mitigation and DNS server mitigation and brackets the traffic at one level in the kernel. Is that so?
Currently that's not the case. Is this mic working by the way? It doesn't really sound like it does. Okay. We don't use both because they are configured in so different ways, and we want to get away from the current very labor-intensive configuration. So currently the answer is no, we do just one. I'm wary, I would say I haven't checked, so this is something we could investigate, but I'm wary that they would actually work against each other rather than helping each other unless you were very careful in how you configure that. I see potential damage there, but it could be looked into. If there are no more questions, thank you so much.
Thank you.
Thank you.